Are you ready to dive into the world of operating systems? This video explores the essential functions and architectures of modern operating systems, discover how they manage resources and facilitate user interaction with computers. In this section, we explore the role and principles of operating systems. Operating systems manage resources in a computer and are essential for efficient operation. They act as an intermediary between users and the computer hardware, ensuring that programs run smoothly and efficiently. The principal functions include memory and process management. Memory management involves keeping track of each byte in a computer's memory and managing the allocation and deallocation of memory spaces as needed by various programs. Process management is responsible for creating, scheduling, and terminating processes and for managing inter-process communication and synchronization. Trade-offs exist in allocating hardware resources to processes, such as balancing CPU time among competing processes to ensure responsiveness and efficiency. These decisions often require strategies like priority scheduling, time slicing, and resource locking. By the end, you'll learn to write operating system code at the kernel level. This includes developing low-level code that interacts directly with hardware components, handling system calls, managing interrupts, and implementing core OS functionalities such as device drivers and file systems. Operating systems have evolved significantly since the 1940s. Initially, there were no operating systems, and users manually managed hardware. Batch processing systems improved efficiency by automating job queues. Multiprogramming allowed multiple programs in memory, enhancing CPU utilization. Time-sharing systems enabled multiple user interactions with central computers. A modern operating system manages a computer's hardware and software. It allows safe and efficient interaction between users and machines. Acting as a bridge, it ensures that applications can access hardware resources without direct control, thus improving stability and security. Key functions include managing processes, memory, files, and devices. Process management ensures that multiple programs can run simultaneously through scheduling and context switching. Memory management allocates RAM efficiently to avoid crashes and ensure performance. File management organizes data storage, access permissions, and directory structures. Device management handles input-output operations through device drivers that standardize communication. It also handles security, networking, and error detection. Security mechanisms include user authentication, access control, and data encryption. Networking capabilities enable communication between computers over local or global networks. Using standard protocols, error detection and handling ensures that faults in hardware or software are recognized and managed gracefully. For instance, when opening a program, the OS manages memory and CPU time automatically, loading the application into RAM, assigning it a process ID, and allocating processor cycles as needed to ensure smooth operation. At the core of an operating system is the kernel. It directly controls hardware and performs low-level tasks like memory allocation. Above it is the shell, which users interact with. System libraries and utilities help applications communicate with hardware. This architecture transforms hardware into a working system. Operating systems are essential for interacting with computers and mobile devices. Windows is known for its user-friendly interface and compatibility. macOS offers strong security and sleek design. Linux is open source and favored by developers for its stability. Mobile operating systems like Android and iOS dominate the market. In the early days, computers had no operating systems. Users managed hardware manually, which was inefficient and error-prone. Batch processing systems automated job queues, improving efficiency. Multiprogramming allowed multiple programs in memory, enhancing CPU utilization. Time-sharing systems enabled multiple user interactions with central computers. The kernel is the core part of the operating system, managing resources and communication. Process management handles creation, scheduling, and termination of processes. Memory management allocates and deallocates memory space as needed. Device management uses drivers to manage input-output devices. System calls facilitate communication between user programs and hardware. Process management assigns CPU to processes and manages multitasking. It coordinates the execution of multiple programs, allowing users to run several applications simultaneously without interference. It uses algorithms to determine which process runs when. These include scheduling algorithms such as first come first serve, FCFS, round robin, and priority scheduling, which help optimize CPU usage and system responsiveness. Ensures process synchronization and communication. Synchronization mechanisms like semaphores and mutexes prevent race conditions by controlling access to shared resources. Inter-process communication, IPC methods, such as message passing and shared memory, allow processes to exchange data and coordinate actions efficiently. Handles deadlock prevention and resolution. Strategies such as resource ordering, Banker's algorithm, and preemption help avoid or recover from deadlocks where processes wait indefinitely for resources. This component is crucial for efficient system operation, as it ensures fair resource distribution, maintains system stability, and maximizes performance under concurrent workloads. Memory management tracks each byte in RAM and allocates memory to processes. It deallocates memory after a process completes, uses techniques like paging and virtual memory, ensures efficient use of memory resources. This component is vital for system stability and performance. File system management organizes data into files and directories, controls how data is stored, retrieved, and secured, maintains metadata like file size and permissions, provides access control, and ensures file system integrity. This component is essential for data management and security. Device drivers are specialized programs allowing OS to communicate with hardware. They abstract hardware complexities and provide standard interfaces. Each device has its own driver tailored to its functionality. Drivers manage input-output operations. They are crucial for hardware compatibility and performance. User interfaces explained. The user interface enables interaction between users and the operating system. Command line interfaces offer text-based interaction. Graphical user interfaces use windows, icons, and menus. Both interfaces translate user inputs into commands for execution. They are essential for user-friendly operation. Security ensures that access is granted only to authorized users. It enforces authentication and authorization protocols, protects files and memory from unauthorized access, includes firewalls, encryption, and audit logs. This component is vital for protecting system integrity and user data. Networking handles data transmission between devices over networks, supports protocols like TCP/IP for communication, enables services such as remote login and file sharing, manages data flow to ensure reliable connections. Networking is essential for modern interconnected systems. Operating systems manage hardware through processor, memory, and device management. CPU scheduling allocates time to processes. Memory management tracks and allocates RAM. Device management uses drivers for input-output operations. Storage management controls data storage and retrieval. These functions ensure efficient hardware utilization. The OS manages software processes and application needs. Process management handles the lifecycle of processes. File system management maintains file structure and access. Security enforces user authentication and access rights. User interface management translates user inputs into commands. These functions ensure efficient software operation. Operating systems are categorized by hardware environment and user needs. Batch OS executes jobs with minimal user interaction. Time-sharing OS allows multiple users to share resources. Distributed OS manages multiple computers as a single system. Network OS provides services over a network. Real-time OS responds within specific time constraints. Mobile OS is optimized for smartphones and tablets, focusing on efficiency. Examples include Android and iOS. Embedded OS runs on devices like ATMs and smart appliances. It is optimized for specific tasks with minimal resource use. Both types are crucial for their respective platforms. Operating systems balance performance, efficiency, and complexity in resource management. Efficiency maximizes resource use, while fairness ensures equal distribution. Responsiveness prioritizes user input speed. Affecting throughput. Simplicity eases maintenance but may lower performance. These trade-offs are crucial for optimal system operation. Caching boosts performance by storing frequently accessed data. However, cached data may become stale, affecting consistency. Preemptive scheduling improves responsiveness but increases overhead. Non-preemptive scheduling is simpler but less responsive. These strategies balance speed and data integrity in operating systems. In conclusion, operating systems have evolved into complex systems that optimize resource usage. Over time, they have incorporated advanced techniques such as virtualization, dynamic resource allocation, and energy efficiency to meet the growing demands of modern computing environments. They provide robust platforms for diverse computing needs, from servers to smartphones. Whether supporting enterprise-level cloud services or enabling mobile applications, operating systems ensure reliability, scalability, and performance across a wide range of devices and use cases. By managing hardware and software efficiently, they make computing practical and accessible. They abstract hardware complexities and provide user-friendly interfaces, allowing developers and end users to focus on tasks rather than system internals. Understanding these systems is crucial for leveraging technology effectively, as it enables users to troubleshoot issues, optimize performance, and contribute to innovations in software and system design. Thank you.